So this question asks us to approximate log base 2 of 3. So let's think about what this means first. If I say log base 2 of 3 equals x, and my goal is to solve for x, we know that the base is 2 and we know the exponent is 3. So 2 to the x equals 3. And I can solve that on the graphing calculator. Simplest way to do that would be to say 2 to the x minus 3 is 0, and then let's use our 0 finder to try to identify that. So let's go ahead and do that. Let's graph 2 to the x minus 3. And let's find out when does that equal 0. I will do zoom decimal. See what that looks like. When do we get 0? There, between 1 and 2. Let's use our 0 finder. And then again, we recognize there's the left bound to the left of the intersection point. There's the right bound, guess, and we get about 1.585. Now that's just one way to think about it. There's a couple other ways we could have thought about that. So that was solving it with the graphing calculator. Again, log base 2 of 3 equals x. The base is 2, the exponent is x. 2 to the x equals 3. I could solve this using algebraic techniques. Let's take the natural log of both sides, right? Natural log of the left, natural log of the right. So natural log of 2 to the x equals the natural log of 3. We'll pull this x down in front. X times the natural log of 2 equals the natural log of 3. And now we have an exact answer, dividing both sides by natural log 2. We get x equals natural log 3 divided by natural log 2. We hope is the same as 1.585. Let's take a look. So upstairs we have natural log 3. So here's again, this is an exact answer. Divided by natural log 2. And what do we get? About 1.585. So that makes me feel pretty good. And then there's one last shortcut way to do this, and that's the change of base theorem. Change of base theorem. If I have log base b of q, you can use a different base, like for example, log base 10 or log base e, natural log q over natural log b, or log base 10 of q over log base 10 of b, or any base you want. Or log base 7 of q over log base 7 of b. So that works. I'd like you to know why, right? That's helpful to know why. So I'm going to use the change of base theorem, log base 2 of 3. You take the natural log of 3 divided by the natural log of 2, and you'll notice this is exactly what we said before, right? And we get our answer directly with the change of base theorem. So the next question I have is log base square root of 5 of 70. So if we use the change of base theorem first, all that would be natural log 70 over natural log square root of 5. So let's go ahead and do that on the graphing calculator. Upstairs, natural log 70 divided by natural log square root of 5. Whoops. Delete. And delete. Put the parentheses on the outside. There we go. And we get 5.279 approximately. Now let's try it in a more algebraic fashion and see if we get the same thing. So that was playing with the change of base theorem. What I have again is log base root 5 of 70 equals x. So the base is root 5, the exponent is x. Root 5 to the x equals 70. Root 5 to the x equals 70. If I wanted to solve this on the graphing calculator, I would say root 5 to the x minus 70 equals 0. I hope my answer is 5.279. Let's take a look at the graphing calculator and see what we get. Go to y equals. We want the square root of 5 to the x power. Order of operations gets tricky. Square root of 5 to the x power. Minus 70, I want to see when does that equal 0. And I think I'll go with Zoom standard. Zoom decimal would probably work. I think I went to Zoom standard. I think I hit 6. Let's see what we get here. Again, we expect it to hit somewhere between 5 and 6. It does. I don't like it looking almost vertical. When that happens, I greatly increase my y min and y max. So we can do that, multiplying by 5 maybe. Times 5. Just don't like the line to look vertical. I like to see it move from left to right so I can find my left bound and my right bound. And again, we're looking for 5.279 as the answer. That's a little better. Second calc, left bound 0 is what we want first, of course. Left bound, move the little cursor just to the left of where it crosses. It's going to take us a while to get there. There we go. A little bit to the left, enter. A little bit to the right, enter, and guess. 5.279, which is what we said before, right? 5.279, we got that from the change of base theorem. Of course, the other way to do this is to look at root 5 to the x equals 70. Hit both sides with a log. It could be log base 10 if you want, because that's also on your calculator. But I will use natural log, so it'll be consistent with what I had before. Root 5 to the x equals natural log 70. We're going to pull the x down. So I get x times natural log 5. Root 5, excuse me, equals natural log 70. And I divide both sides by natural log root 5. And you can see my answer that I did with change of base theorem shows up again. X is natural log 70 over natural log root 5. By the way, natural log root 5 is the same as natural log 5 to the 1/2. Is the same as 1/2 natural log 5. So I can make this a little prettier by taking natural log 70 over 1/2 natural log 5. So just another equivalent way to write that one.